with extensions or with magnetic stands, or some special devices. Maybe you heard about the 3D quickset measurement structure. That's also a device where we can use for measurement. So, yeah, that's some examples for magnetic stands or various extensions. If you bring it to spindle screws, spindle, some screws at the machine, or here small magnetic stands with extensions. So what should you know by now? Yeah. So here we see now the column angle, T-angle, tube pipe, however you will call. So we call it T-angle in our plant. So here is it visible a little bit better than before. You see that two locks that will go inside the T-slots in the NC round tables. And also we have magnetics on the top. Or sometimes we have the magnetic on the bottom side. Sometimes different. On the right side we see the frame square angle. In that case, that is a kind of stone. So later on I will show it a little bit nearer with the camera, because also frame angles have some tolerance, or some manufactured tolerance. So measurement with the measuring angle or the T-angle. The basic of our measurements with the T-angle is the cross angle of the machine. So cross angle, we will hear it the whole week or the whole training. That is I think one of the importance angle that we use here in our machines. So that cross angle is the basic, and that has to be first measure the parallelism between the x-axis and right angle to the y-axis. Sometimes it depends on the machines, and also sometimes we have to look where is our 0 point or the machine 0 point of the machines. There I will show you later on also some machines that can have a different 0 point, machine 0 point. Best thing is that you have not much gyrations and structure, fixture, die gauges or something, so then you can exclude measurement failures. So here is an example with a T-angle and how to measure 90 degrees deviation and from the basic. But that one we will show you tomorrow with our practice. Then we will show it on the tour block machine here by side. Maybe after the break I will show you the machine that we have here in our training room. So reverse measurement to check an angle. Frame angles cannot be checked for reversal since the same measuring surface not be traversed. Yeah. So that means the D angle, when we set it on the round table in the middle, so we can use also the C-axis and can, for example, move it 180 degrees and measure it out the failure from the C-axis, for example. And if you see A-axis, maybe A side is 5, yeah, you have always the error of 5 microns that you have to measure out and take for your whole, calculate the difference for 5 microns with your whole measurement. Okay. So I think I have to try my dry voice. I will make it a little bit wet. So I need a coffee now. And I think maybe you too. So we will do another coffee break and meet us in 10 minutes. It's okay for you? 90 degrees in that way. That's a grinded tool. And also for that tool or for that equipment, you have to be careful about it. If it fall down, you have to measure it because it can have a bad run out or something else. And also you have to be careful that the grinded surface is not rusty or damaged with chips or something if you have to use it here. So very important thing that we use that tool with a good cleanness, and also that the surface is clean. And also after we use the mandrel, we have to protect it about sweaty fingers or some that we have to be prepared with some, how is it called, some oil or CRC. Kannst du das Licht nochmal aufmachen? Thanks. Also, if you use test mandrel, be sure that you have a good case for it, that it will be not damaged in transport or something. So measurement with a test mandrel will be made as a reversal measurement to a sign that the error is mostly the run out of the motor spindles. No problem. So run out or concentricity measurement is very important. So because if you only measure with the mandrel in one position, then you have not the correct run out of the motor spindle. So, sorry? Yeah. And to find the run out the correct, so we use the mandrel in per position. So in that case, first we see it to measure out the right angle, but to measure out the run out from the spindle, we have two different measurements to do. So the best thing is I show you at that page. So normally when we do a spindle run out, we measure it in 8 positions. So we use it one in the 0 position, in a range 20 millimeters from the spindle nose and up to 300 millimeters from the complete length of the test bar. So we measure it with 0 position or 0 degrees position. We mark it and then we do 4 times the same 90 degrees step. So, and if we summary that one, we have sorry? Yeah, then you calculate that 8 measurements divided by 2 and you have the complete runout from the motor spindle. So that sheet you can use or you can copy out, or sometimes I think also in every measuring protocol from the machines, they will be also shown that measurement. So if you have, for example, a collision on a machine, so then I told you before we have to check the runout of the z-axis or the movement of the axis, but also we have to, I think the first step is to measure the spindle concentricity. And if we have a bad runout of the spindle, you can stop the complete measurement and change the motor spindle or any other spindle. Maybe not. Some machines here we have mechanical spindles. I think Seebach plants use it. So in that way, you can figure out is there a failure or not, and also the tolerance of the spindle. So mostly tolerance 20 microns run out, but in that way, sometimes you have customers, if you will have very accurate workpieces also, and you go near to the tolerance border, then we have problems. But then we have problems with the kinematic, and the failures, and also the workpieces will be not right in tolerance. So then in the first, I think mostly, you have an half tolerance around, or maximum I will say 15 microns. So that's one something that I told. Was steht da? Hanko, müsstet ihr so anlassen? Mal lassen. Okay. So that was that PowerPoint. I will share later on. Degree of freedom of manual machine tool. eingegangen drauf nicht, oder? So kinematic machen wir nicht, geometric basic. So we will continue in that sheet. This is the PDF. Yeah. For example, we see here now a monoblock machine, and that's geometric basic or relation between the main axis. And if we see main axis, 5-axis machine, in that case we have a swivel round table. That means I have the Z-axis, C-axis, we have an A-axis, we have a vertical axis, that means Z-axis, we have a horizontal axis, that means the Y-axis, and that means the square axis is the X-axis. So in that case, we had some points where the machine is fixed, or that different bodies are fixed. So we have one big machine bed. There we have a fixture for the swivel round table. It's around here on two sides. And then we have two rail guides for the Y-axis and 4 machine or radar guide shoes. And now we come a little bit deeper for the X-axis. We see we have 2 rail guides for the X-axis. Dual block we have 3 rail guides and also 2 machine shoes. And we have a connection with the spindle milling head or something. There we have vertical rail guides here. So in any case, it doesn't matter which machine you have, if it's the CO or an AG machine, you have to know, or you have to be sure which axis are the basics and which axis are the basic for the cross angle. And also, I can so from my experience on the AG side, the basic is mostly, I say mostly 80% the Clemao machines are the basic is the table. So the table means, yeah, basic table, we have a swivel round table in that case. So there we have to look, is it in Y-axis and X-axis way, in the right angle and particularity. So that's one of the important thing. And then the next step is the Z-axis. So then we have the cross angle like here. So this coordination cross is not the same like the cross angle that we have to find out or measure out for our machines. Yeah, here we see the example for the monoblock. So this is a monoblock example at side with a round table, a pellet system that doesn't matter now in this case, but you see we have a swivel round table, in that case with a pellet on a table or a pellet carrier. In that case, the pellet carrier is our basic for that machine. So that for beginning or to find out after collisions or repair or if you have replaced rail guides, bearings, motor spindles, anyway, which part was damaged, then we have to start with the basic, and that's the table. So we have to start with the runout. Sometimes in measurement protocols, the first measurement was the centric brush inside. So that's not so the important thing. I think I will say basic is the runout, and then the parallelism X to Y. So, yeah, that sentence you can also remind the accuracy of machines very strongly depends on the machine geometry, and that means it is the complete mechanical side. So if that's okay, then you can software use some compensations. That's the other thing. But how good is the mechanical geometry? How less is the compensation? And that gives you a good result of any machine. So here also a thing that we can have an influence. Yeah, rail guides, you know, I think any machine has it here in the plant in different sizes. But I didn't know if you hear about that 3 rotations that we can have from the shoe to the rail guide. And that means from the x-axis we call it rolling. On the y-axis we call it pitching, and on the z-axis we call it shaving. And yeah, if you have too much gap in the shoes or something, you have maybe that one of that cases can happen, and then that's a big influence of your geometric. So yeah, general measuring sequence. First, check the straightness, then the concentricity and the runout, that means the middle brush inside. Check the perpendicularity and check the parallelism. So that's the general measurement sequence. Measurement sequence after collision. First, check the table runout. Check the spindle concentricity with the test manual, and then check the straightness of the guide tracks. So in that case, you can use a frame or also a test bar to measure the straightness of the guides. So, and if that 3 measurements are in tolerance, everything's fine. If we have bad tolerance in spindle concentricity, you have to first replace the motor spindle or the main spindle. If you have to check the table runout and there is a failure or a failure seen, then you have, for example, to no, maybe you only unlock or unstress the bearing the first step, so you lose every screws from the bearing from the table or from the pellet carrier, and maybe you go with a rubber hammer or a hammer to stress out some tensions of the bearing. Then we can retie all screws from the bearing. And the most thing from my experience, if the bearing is not worn out, then the concentricity or the run out will be back in tolerance. Same is if we see we have some straightness of the guide tracks. So also maybe we will show it tomorrow when we do it on the machine. Then we will see, yeah, sometimes you, for example, you move with your dial gauge on the test bar or the frame or the T angle, and you see the last 10, 15 millimeters, you have a rise up, or you have a value. For example, you measured 500 millimeters, and the last 100 millimeters, 400 millimeters, it was in tolerance, and the last 100 millimeters, you go out of the tolerance. That is be a sign that something is wrong with the rail lights. Okay. Jetzt bin ich da schon mal durch. Okay, so any questions so far? Or I will question here in the round. Mal das Teil aus. So is it understandable so far, or is there any questions open, or?
Well, this is good information. I feel like we all should have gone through this class a couple years ago. You know?
Yeah, I was gonna say I feel like this class should have been had right when we all started at the company, not 4 years later.
Yeah, but I know guys that have been doing this for 10 years that don't do this shit. You know, they just put the square on there, run it up and down. They don't even know what they're checking half the time. You know, they just throw the square on there, run it, write the number down. Don't give a fuck. You know.
I know. Yeah. Yeah, I understand. This is an organization thing, you know. I'm also not so happy. I will show normally this part of thing live to you, and not with an online training or something. So, but anyway, you look at here also. If you go to Garrett Street, my colleague over there, he also a very experienced guy, and he also knows, yeah, where are hidden the failures for the measuring. Sometimes I know things, and I know service engineers. They say, what the fuck, I do it now 10 years, and then 10 years was the wrong size. But anyway, the machines, or after your service task, the machine has to be in good conditions, and sometimes it's also the way how you do it is to find it out by self or learning by doing. But deeper informations like here in that training, yeah, normally it has to be start if you begin here. But that's, yeah, organization thing and not so good. Yeah, it is what it is, yeah. Okie doke. So then, was machen wir als nächstes? Yeah, now I will show you an protocol of a DMU 82, a block machine. Just a moment. Na, da ist es. Das muss ich nochmal zurück. Messkurs. Und die Protokolle. Yeah. So if you're not so long here at our company, or maybe time, sorry, I forgot to share. So I hope now you can see it.
Yes.
Yeah, okay. So that's the accuracy test result protocol from a new type dual block. So that means